Hi, Mr. Corsi here. In this video we're going to prove de Moivre's theorem. And there is the theorem. The complex number cos theta plus I sin theta is on the unit circle. The modulus is 1 and we raise it to the power n. We also get another complex number in the unit circle which has argument n theta. And this statement is true. We're going to prove it for all positive, negative integers, including 0. So how do we do that? First stage, we'll prove it for the positive integers. And we'll use mathematical induction to do that. The next step, step 2, we'll prove the specific case n equals 0. We'll deal with that before launching into step 3, which will prove the statement for all negative integers. So, first of all, the positive integers, that's step 1. Mathematical induction. Here's an analogy. How do we know all these dominoes are going to fall? We first of all have to know that the first domino falls. And thereafter, if we pick any domino, we have to know that it's close enough when it falls for the next one to fall. So, for instance, domino 6, if it falls, it must knock domino 7 down. In this case, k is 6, k plus 1 is 7. It works with, say, k equals 5. We look at the 5th domino. It's close enough to knock the 6th domino down. The 8th domino will knock the 9th domino down. It works all the way along. So these two facts have to be true. We must know the first domino falls, and we must know they're close enough so that if we pick any one and it falls, then it'll knock the next one down. So how does that help us understand induction? We're not looking at dominoes, but we are looking at the truth of a list of statements. So by analogy, the first domino is the first result. Is it true? We have to show that. And if we pick any result and pretend it's true, then it must mean the next one's true. That works all the way down. 6th one's true would mean the 7th one's true. 7th one is true would mean the 8th one's true, and so on. And therefore, falling down the dominoes is like truth running through these results. So there's two stages. We prove the first statement's true. If the kth result's true, then we can show the k plus 1th result is true. If these two things can be shown, then by induction all the results will be true. So let's start the process. So cos theta plus I sin theta to the power 1, does it equal cos 1 theta plus I sin 1 theta? Well, I think it's self-evidently true. Definition of raising to the power 1 just gives you the same complex number, and of course theta is just 1 times theta, so certainly result 1 is true. So let's now look at the second stage of the procedure. We know the first domino, if you like, falls. We now look at the kth result and pretend it's true. Can we then prove that the k plus 1th result is true? Well, let's look at the k plus 1th result. Here we have cos theta plus I sin theta to the power k plus 1. Now, by our laws of indices, that's the same as cos theta plus I sin theta to the power k times another cos theta plus I sin theta. And we are pretending that we know, this one was by the index laws, we're pretending that we know that cos theta plus I sin theta to the k is cos k theta plus I sin k theta, what they call the inductive hypothesis. So we can use that inductive hypothesis, assuming result k is true, and then we get the product of two complex numbers. And of course there's the rule that we add the arguments when we multiply two complex numbers in polar form. So that's the multiplication rule, adding the arguments. And of course k theta plus theta That's k plus 1 lots of theta. K theta plus another 1 theta is k plus 1 lots of theta. And there we have it. Cos theta plus I sine theta to the power k plus 1, that index k plus 1 now becomes a factor k plus 1 in the argument. So if we pretend result k is true, then we've shown that result k plus 1 is true. Hence, by mathematical induction, all results are true, in this case, where n is a positive integer. Result n is true where n is a positive integer. So first domino falls, result 1 is true. If a domino falls, it's close enough to knock the next domino down. Result k is true, means result k plus 1 is true. So let's move on to step 2, which is the special case when n equals 0. So let's now look at what that result would be. We would have cos theta plus I sine theta raised to the power 0. That would equal cos, and remember the index goes down and becomes a factor of the argument. So it would be cos 0 theta plus I sine 0 theta. So is that result true? Well, let's have a look at the left-hand side of the result. Cos theta plus I sine theta raised to the power 0 by definition is equal to 1. That's the definition of the index 0. So let's look at the right-hand side. And there we've got cos 0 plus I sine 0. And remember, cos 0 is 1 and sine 0 is 0. So that again gives us 1. So the left-hand side does equal the right-hand side, and therefore the result is true for n equals 0. So that completes our step 1 and step 2. Step 1 was, remember, for the positive integers, and step 2 was for the special case n equals 0. So we'll now move on to step 3, which is to prove de Moivre's theorem for the negative integers. So let's have a look at the expression cos I sine theta to the power n, where we now know we're concerned with n being a negative integer. Now it's true that if you have, for instance, let's take negative 8, we can always write a negative integer as a positive integer times negative 1. So in this case, let's take n, a negative integer, and write it as m times negative 1. And the important fact is that m is now a positive integer. And let's look at this expression again. So cos theta plus I sine theta to the n, a negative integer, can be written as cos theta plus I sine theta to the power m times negative 1, where m this time is a positive integer. Now another fact about indices, when we're multiplying indices, let's remember x squared cubed. That's x to the power 6. We multiply the 2 and the 3 together, so we can rewrite this as cos theta plus I sine theta to the power m, and all of that raised to the power negative 1. Now look at cos theta plus I sine theta to the power m. M is now a positive integer, so we can use de Moivre's theorem because we've proved that for positive integers. So that becomes cos m theta plus I sine m theta to the negative 1. The meaning of to the power negative 1 is 1 over that complex number. So we've got 1 over cos m theta plus I sine m theta. Let's simplify that. And the usual trick is to multiply it by cos m theta minus I sine m theta over cos m theta minus I sine m theta. That's the conjugate of the denominator there. So it's multiplying by 1 basically. And on the top of that fraction, we'll get cos m theta minus I sine m theta. And on the bottom of the fraction, multiplying these two together, the inside-outside terms disappear, and we've got cos squared m theta, and then we have a plus sine squared m theta. And that gives us 1 on the bottom. So we just get cos m theta minus I sine m theta. Now, remembering your quadrant diagram, cos m theta is exactly the same as cos negative m theta. Cosine in the fourth quadrant, same as cosine in the first quadrant. However, for sine negative m theta, that's the negative of sine m theta. So the negative becomes a positive there. And we've now got n theta, because remember negative m is n, and there is de Moivre's theorem, where n was a negative integer. So, in summary, the result is true when n is a negative integer. Now let's combine all of these together. Step 1, step 2, step 3 can all combine, and we have, in all its glory, de Moivre's theorem for all integers n. So that's Mr. Carsey signing out, and I hope you enjoyed the video.